All right, let's look at exercise 8 from section 2.7. So the purpose of this one is to basically use this new technique we've learned, so implicit differentiation, to to give ourselves another way to prove a derivative rule we already know. So namely this one here, we know that the derivative of an exponential function is equal to that same exponential function times the natural log of the base. So I think this was actually the first derivative rule we went through, or maybe early, but maybe not necessarily the first. But basically, we have another approach we can get there. So first thing we're asked to do is take our generic exponential function y equals a to the x and rearrange it. So now I want to take a natural log of both sides. So if I have natural log of y equals the natural log of a to the x, or that's actually not what it's asking me to do. Sorry. So it's asking us to use the natural logarithm to rewrite this. So actually, I'm going to go ahead and taking the natural log of both sides is a way we can get there. So the natural log of y equals the natural log of a to the x. One property of logarithms we have is that if we take a log, any log, of something raised to a power, that's equivalent to this. Instead of raising a to that power and taking the natural log, we can take the natural log of the base by itself and multiply that by whatever x is. So now we are asked to figure out, or we're asked to write x in terms of y. Okay, so essentially we want to solve for x. So get x equals the natural log of y over the natural log of a. So for part A, we want to make that rearrangement, and I think we've done it. So part B, differentiate both sides of the equation you found with respect to x. So we have x equals the natural log of y over the natural log of a. To make this easier to take a derivative of, I'm going to rewrite this. Because it might be tempting right now to use the quotient rule. I'm actually going to avoid doing that because I think the quotient rule is really powerful for if you have a fraction and you have variable functions both in the numerator and the denominator. We don't have that right now. Natural log of a is a constant. A is unknown to us, but it's not variable. It is a constant. So what I'm going to do instead is write this as 1 over the natural log of a times the natural log of y. And my next step here, I'm going to differentiate this equation, both sides of it, with respect to x. So what's the derivative of x with respect to x? That is by the power rule from 1. I have a multiplied constant, so I'm going to go ahead and just carry that constant with me. Now, what is the derivative of the natural log of y with respect to x? So we have to use the chain rule here because we have an implicit differentiation application. So we'll rely on this fact here that the derivative of natural log of x is 1 over x, which means the derivative of natural log of y with respect to x, we have to handle in layers. The derivative of natural log of y is going to be 1 over y when we handle the outside function there. But then when we handle the inside function itself is y. So what is the derivative of y with respect to x? That's what we call dy dx. So we differentiated both sides, and I don't think the purpose on this one is to simplify. But yeah, so the derivative is now done. So part C, all right, so now we want to solve for dy dx. So even though part C is on another slide, I'll just rely on my work here. So now I want to isolate dy dx. So how do I do that? I'm going to multiply both by natural log of a and y. So that'll give me this. Dy dx equals y natural log of a, which is correct, but I don't want to leave this as, I want to find dy dx, and I want the right-hand side to be only in terms of x. The only variable I want to look at is x. So what do I know about y? Well, very, very early, we said that y was equal to a of x. So I'm going to go ahead and make that substitution now. Y is equal to a to the x, then we have dy dx equals a to the x of the natural log of a. So again, just another approach to basically prove a derivative rule you're already aware of, but yeah, implicit differentiation. One of the many things that that I hope I'm emphasizing well is that we've taught you lots of derivative rules. They really all come from the same place. They're all united, even though the way they're presented looks a little different.